Let's start. What is armature reaction? It is almost identical to synchronous machine armature reaction. But in synchronous machine, it is much more complicated due to lagging or leading current. In DC, armature reaction makes an effect as if synchronous machine operates in only ohmic loaded condition. DC machine armature reaction similar to ohmic synchronous machine armature reaction. So it is easier here. Okay, let's start. What you see in the picture. Here are some that is totally stator. That is totally rotor. On stator, you see some poles. Let's say main pole. One, main pole. Two, main pole. Three, main pole. Four. That is a four-pole machine. Four-pole machine. That is the field coil. Field coil or pole coil. That is the pole body. That is the pole face. Pole face. That is the pole shape. And the pole coil is around the pole core. That is the body. Sometimes we say frame. Gövde. And then here are something more, which is here are tiny poles, and tiny pole windings, something like poles. Yes, they are interpoles. Ara kutuplar. Bazen de auxiliary poles diye geçer. Yardımcı kutup. Interpoles, ara kutup. Auxiliary poles, yardımcı kutup. Bazen de commutation poles. At the end of this course, we will discuss why we use such interpoles for making easy commutation. Commutation değişim işlemi, akımın değişim işlemiydi. Bunun bir zorluğu var. Kolaylaşması için işte bu tür yardımcı araçlar kullanıyoruz bazen. Bunun dersin sonunda anlayacağız. Ama bugün gelebilir miyiz bilmiyorum. Here you see armature winding. Armature winding. Windings. Lots of winding. Here are commutator. Commutator segments. Multiple segments you see. All coil ends are connected to commutator segments. There must be at least two connections in each commutator segment. Here's the shaft you see. Nothing more. Here are liners. Insulation material. Insulation materials inside the iron core, because those are iron sheets you see. Sheeted material, laminations. Here you see the same type of machine. Here is the main pole, but there is no interpole or auxiliary pole in this machine. It is not a general case. In a high-cost machine, you see interpoles for high-quality machine. In everyday machines, in a cheap machine, you see simple construction. You see a four-pole stator. 1, 2, 3, and 4. Here are the poles. Cannot be seen clearly. That is the frame. Let me change the color. frame. That is pole core. Pole core. Totally it is called as pole. That is pole winding. Pole winding. Pole winding is sometimes called as field winding or field coil, because you see a simple coil. For example, o biti biti, karamela, sepeti, terazi, elastic, gymnastic. Here are two ends of the coil. That's a simple coil. And over the pole core. All those construct a magnetic pole. And here you see 4 pole in stator. We simply represent all those coils in the field system. Generally, we connect them series. Let me show you. Here's a coil connected to series. Here's another. Here's another. And then here are 2 ends. Let's say field 1 and field 2. Field 1 and field 2. Those are the terminals. We simply represent that system as a simple winding. That is pole winding, field winding. We apply DC. Many times we use adjustable field voltage to control field current here, because field current produces field in the pole. If you control field current, you can control field, and EMF can be adjusted easily by field current, and torque induced in the machine can be adjusted easily by changing field current. Field current results in some change in magnetic field, and it will cause a torque change or EMF change. In the conversion system, machine conversion will be affected by magnetic field and field current. And you know, magnetic field is a vectoral quantity. It has got a magnitude and it has got a direction. It is a vectoral quantity. So here is armature. It is rotor or armature. Rotor carries armature winding. You know, armature is the place where the electromotive force or energy conversion occurs. Here is the armature winding. Here are the ends connected to commutator. And here are wedges, fiber wedges. Here are multiple to keep conductors inside the slot to overcome centrifugal forces. Due to centrifugal forces, the conductors in the slot try to leave the slots due to centrifugal forces. So you insert some fiber wedges here. That is the fiber wedge. Fiber kama diyoruz. Kama wedge. Kama. Buraya insert ediliyor ve merkez kaç kuvvetlerinden dolayı bobinlerin dışarıya doğru püskürmesine ve ambalans yapmasına ve izolasyonun bozulmasına falan engel olmuş oluyoruz. Here is the equivalent circuit of the armature, Houston, and that is the new topic, armature reaction. First, apply only field current to pole winding. Here you see, when you apply some current to poles properly, apply right-hand screw rule. Let me show my camera. I only examine this guy here. Current is entering the screen by my right hand. Forefinger represents the magnetic field's direction. Take care this screen camera. That is my right hand. That is the current flow. That is the magnetic field flow. So here is such a field direction. And let's examine this guy. Current is towards to me, and then 4 fingers represents magnetic field direction. That's it. I switch off my camera due to mount width. Here you see magnetic flux distribution. Here are equipotential lines. You know, flux lines are always perpendicular to equipotential lines. So such a travel will occur inside the machine. That is field flux. That is d-axis in synchronous machine. Here it is as well. D-axis, pole axis, magnetic field, main magnetic field axis from N to S over rotor or armature. There's a smooth distribution. You see only field winding excitation. Okay, do not forget this. And then let's talk about armature coils. I have told you earlier there were 2 coils and S between the magnetic poles N and S. There is no magnetic field yet. Just think the things I have written on the right hand side. N and S. And here's the same coil in a horizontal position. This guy will induce maximum EMF. This guy induce 0 EMF. EMF will be 0 if it is a horizontal position. So maximum EMF result in maximum current. Houston, current will be here if there is only 1 coil. If there are 3 coils, current will be like this. Okay, what is the rotation direction? Let me discuss a little bit. Okay, I have calculated. That is the rotor direction. Let me switch on my camera and then apply left hand 3-finger rule. That is my left hand. Assume that there is M pole on the top of the rotor and S pole on the bottom of the rotor, and magnetic field with your mid finger from N to S. That is the rotor's conductor direction. That is the resultant current direction. I mean E equals to BLV with your left hand 3-finger rule. Magnetic field N to S. That is the moving direction of conductor. That is the resultant current. So it is into the board. Second case, only armature current exists. Just assume. In fact, there is no such a case. In fact, there will be no electromotive force induced because there is no magnetic field in the poles yet. But just assume. For example, you can assume that you have applied an external electric power to the armature. There is such a current. Such a current will cause such a magnetic field. Okay, let me switch my camera on again. Here are some crosses. Here are some dots. Okay, let me show right hand thumb rule, screw rule. That is the current direction. That is the magnetic field direction. Let me draw here. That is the magnetic field direction. Due to such a current flow, cause some magnetic field. And the bottom one, this one, current towards to me and magnetic field in counterclockwise direction. That is the magnetic field flux. Those are something like that. It is just pure on quadrature axis. Houston, here were the axis, Here were no magnetic field in quadrature axis, but when there is a rotor current, Houston, there is an armature MMF. Aha, there's a distortion in the magnetic field. Take care. In the beginning, there were field MMF downward in the direct axis, as you know from synchronous machine theory, and then you have applied some armature reaction in quadrature axis. Here you see, and then there is a distorted flux in a new direction. Ta-ta! That is the resultant F. F, you know, F over reluctance makes flux. That is MMF over reluctance cause flux. Here you see some flux lines, distorted. Distorted, I mean, here were uniform distribution. For example, you see uniform distribution. And you observe distorted, not uniform distribution. Due to more dense region here, flux will be larger in a smaller cross-section area. B will be larger, B will be saturated. Houston, here would be saturation, would be saturation. There is no problem, but here would be saturation. Again, some other problems will occur inside the rotor, but it is not clearly seen here. Again, here are saturation. And saturation cause flux drop, EMF drop, and torque drop. Houston, when there is a flux drop, the other elements will be affected. Machine will go under a new equilibrium. Here is the happenings. First d-axis, then quadrature axis, and then that is the result. That is the F net or resultant. That is the armature reaction. Okay, let me repeat what armature reaction is. Armature reaction is the phenomenon, a natural event caused by armature current. If there is armature current in the rotor, that current will cause a quadrature axis MMF. It is on quadrature axis. That quadrature axis MMF interact with d-axis field MMF.
You are currently the only person in this conference.
And then resultant flux will be distorted. That interaction called as armature reaction. Armature reaction. Armature current makes armature reaction. Armature current cause armature reaction. If there is no armature current, there is no armature reaction. If there is high armature current, there is high armature reaction. It is similar to what it was in synchronous machine, but armature reaction occurs only in quadrature axis. There is no d-axis component, so it is much more simple than what it was in synchronous machine. You remember in synchronous machine, in leading or lagging current armature reaction events, there were some d-axis component of the armature reaction causing some more distortion. But I need to define something new. In Turkish, we say pole axis, kutup ekseni. Pole axis. Kutup ekseni. Or d-axis. That is the quadrature axis. That is geometrical quadrature axis or geometrical neutral axis. In quadrature axis, sometimes we call magnetically neutral axis. That is magnetic axis, that is magnetically neutral axis. It is quadrature to magnetic axis. It is Q. Now, ladies and gentlemen, that was the previous case. Geometrical neutral axis. Geometrical neutral axis. But, Houston, due to armature reaction, magnetic axis will be diverted and quadrature axis will be diverted, result in a new direction. Houston, that is the new magnetic neutral axis. New magnetic neutral, magnetically neutral axis. It is different than geometrical one. That was a theoretical, geometrical neutral axis. But there's a displacement, Houston. One more figure. Remember, here's a coil. Here is N pole, S pole. That is the another position under N and S pole. Here EMF is 0 and here EMF has maximum value. Now, again, remember commutation process. Those two guys are connected to commutator segments. Here's, let me show you such a half circle. Those are commutator segments connected to that coil. When it rotates in a horizontal position, the half circles of the commutator would be like this. The A side will be here, B side, A prime side will be here. A prime, A. Okay, it is rotating in counterclockwise direction. So, here are half cycles. Take care, ladies and gentlemen. Here were brushes to pick up EMF outside. Here are brushes to pick up voltage. And brushes are stationary. Here is the brushes. Ta-ta! Causing some short circuits, ladies and gentlemen. It's dangerous. What is the danger? Here you see brush cause some short circuit between the segments. Houston, we've got a problem. Here would be spark. Zzz, zzz. And we must have a solution for this. Ladies and gentlemen, don't be afraid of this. You said there is no electromotive force when it is horizontal. Yes. If there is no electromotive force, there will be no current. If there is no current, there will be no spark. No current, no spark. That was good before armature reaction. Ladies and gentlemen, when there's armature reaction, ta-ta, magnetically neutral axis will change. But brushes are fixed. Ta-ta, Houston, after the armature reaction, since your brushes are fixed in a place, since magnetically neutral axis has moved at an angle, the electromotive force will not be zero. The electromotive force, Houston, will be different than zero after armature reaction occurs. Houston. So there is spark. Oh my gosh, you said there's no spark and then you said spark. Yes. There will be no spark, but after rotor current, there's a new magnetic realignment. Magnetic neutral axis will have a new position, but your brushes are at a fixed point. So induced electromotive force for the coil under the commutation. Houston. Bak burayı Türkçe söyleyeyim. Tam böyle dönerken değişim anına denk geliyor. Bak şu fırça bu A'ya basarken birazdan A üstüne basacak. Şuradan A'dan A üstüne geçiş anına, komütasyon anına denk geldiği için tam komütasyon anında kısa devre oluyor. Normalde bu sorun olmayacaktı ama endüyo akımı peydahlanınca, enerji dönüşümü yapınca Houston, manyetik nötr ekseni kayınca, alfa kadar atıyorum. Bu tabi depends. Yani şimdi alfa kadar kayar, birazdan 2 alfa kadar kayar. Yani armatür akımına bağlı. Endüyo akımı artarsa armature reaction artar. O zaman da yakalar ki tuta ki. Yani tutamıyorsun yani. Adam hareketli. İşte armature reaction buna cause ediyor. Sebep oluyor. So there is a problem with us to solve, to overcome. That is armature reaction. We will develop some precautions. We make some new designs to eliminate armature reaction effects. There were at least 2 videos related with this. I will find out, I hope. Sparkling. Okay. That is in my playlist. Let me show you again. That's the video, 18th. Let me find out the proper position.
This line through points of zero generated EMF is called the neutral plane.
Neutral plane. You already know this.
Placing the brushes in this neutral plane reduces the tendency for sparking between brushes and commutator.
Here you see commutation process. Here are commutator segments. While it is rotating in a position, for example, something here, the brush will short circuit 2 commutator segments.
You are currently the only person in this conference.
And those 2 segments are connected to a coil. So there is an electromotive force is induced. There will be some sparking. But the coil in these axes, let me show you. Here you see some polarity. If it is, if this coil is vertical position, so there will be no induction.
There is no difference.
If coil is in neutral plane, neutral axis, there will be no induction, so there will be no sparking under commutation.
Potential between these segments.
Because there is short circuit happening just under the brush while it is moving. That is the coil under the commutation. short-circuited coil is under the commutation. Değişim içerisinde. Bobini birazdan akımı yön değiştirecek. So we call the coil under the commutation. Commutation process happens right now. From left to right. But if the coil is in vertical position, in neutral plane, there will be no electromotive force induced in the coil, so there will be no sparking due to short circuit done by brush commutator segment mechanism.
Theoretically, no sparking should occur at the commutator brushes when they are placed in this position.
As you see, the guy explains just what I said. And now you see some current due to load current. So that current causes a distortion in main magnetic field coming from poles.
But the current flowing in the armature loops or coils sets up a magnetic field of its own.
That is the FA or field of armature in just quadrature axis.
This magnetic field interacts with the main magnetic.
Of course, those two magnetic fields will interact each other and cause some distortion. Here you see.
Field and distorts it.
And you see some sparkings. Because new magnetic neutral axis cause some realignment. Realigned. It was vertical, but now it is diagonal.
The distortion causes a shift in the neutral plane and sparking at the brushes. The effect is called armature reaction.
That distortion is called as armature reaction. Due to armature reaction, there is a commutation problem in brushes. Due to sparking, there will be worn out, early aging, and there are some other complicated problems due to armature reaction and commutation issues. Here you see, let me continue.
Sparking may cause severe interference in nearby electronic equipment.
Sparking
may cause severe
interference
nearby
electronic equipments. For example, here you see a radar screen. Due to sparking, there is an interference. Perhaps there will be some error on indication.
There are two ways of maintaining the neutral plane in its correct position.
There are two means to maintain the neutral plane in correct position.
And thus avoiding sparking. It may be done by the adjustment of the brush position.
You can overcome this problem by simply making brush position adjustment. I will show you. Here you see the brushes. Take care. Brush position will be changed into new magnetic neutral axis.
Adjusted to lie in the adjusted neutral plane.
Aha. There's no sparking right now. As you see, you have adjusted brush position. In generator, we move brushes in rotation direction a little bit to keep sparks as low as possible. You adjust, and when you see smallest spark position, you leave the adjustment. You just check by your eyes. It depends the current's magnitude. If there is a high armature current, there will be high distortion. So position of the brushes will be much more leading in such a case. If there is a low armature current, there is no need to move. There is only a small adjustment is enough if armature current is small. But that is a bit complicated. There must be a man controlling the position of the brushes. It is difficult. It is impossible to maintain. So we must make a better design to overcome this problem. Let's continue. And here are something confusing. Let's apply left hand three finger rule in the current situation. These you see my pointer. This conductor is moving upward. Apply left hand three finger rule. Magnetic field lines coming into. Let me switch on my camera. Okay, please watch the camera. That is the magnetic field N to S. That is my left hand. That is the moving direction of the conductor in the magnetic field, upward. So that is the resultant current direction into the screen, current direction. Here you see dot, gentlemen. In those years, let me read the year, 1960s. There's a conflict. They generally show electrons flow direction instead of current direction during that age. So there is a little bit confusing explanations. Only current and electron direction is confused today. They are different. Please take care. That represents electron flow direction, but today we generally show only current direction. Again, let's continue. We should make a new design because the position is not fixed. If there is high armature current, we will make a new realignment for brushes. If there is small amount of armature current, we will make a new arrangement. Magnetic neutral axis will change its position with respect to magnitude of armature current. So it is terrible. Let's check it out. How we make a better design.
The other way of maintaining the neutral plane is by adding interpoles to the generator field.
We can use interpoles. Here are main poles, main pole, main pole, main pole. Between main poles, here are interpoles or commutation poles, or we said auxiliary poles, auxiliary.
These interpoles are small magnets placed between the poles of the main field magnets. The interpole fields oppose the fields created by armature reaction.
That interpoles will be located here on real geometrical and neutral axis will push magnetic field back. Let's see.
The neutral plane is moved back toward the correct position.
Neutral plane moved back to its correct position due to auxiliary poles or interpoles. Okay, now take care. If we change the magnitude of the interpoles with respect to armature current, so we can keep neutral plane in the original position. Let me show you here. Interpoles fed by armature current. Okay, here are poles, main poles. Here is the armature current. Here are the brushes touch into commutator, and then, ladies and gentlemen, take care. Armature current cause some distortion, and magnetic neutral axis will be changed due to armature current, armature reaction. So, one of the methods to keep its original position, here we install interpoles, a tiny magnetic poles, interpoles. So, and take care, interpoles, let me show real situation. Here an ananas ball. Assume that is a generator, operated as a generator. So here is a conductor moving upwards in clockwise direction. So here's the current. Here are the currents. Here are the dots. And then the magnetic field due to rotor will be like this, FA. This is FF. So resultant flux will be distorted in am I right? Let me check. Yes. Yes. Okay. Okay. Take care. Something is confusing. Use your thumb. Magnetic field lines will be like this. Use your thumb. Screw rule. Watch the camera. Current is out of the screen, so magnetic field lines to the downward. Here's it is upward. So magnetic field lines coming from M pole pushed by this. So here will be more dense region. So field lines will be pushed down here and here. So it was here. new magnetic axis will be distorted, will be changed. It is in a leading position in rotation direction. That was the rotation direction. Let me show you. And that is the new magnetically neutral axis. But to overcome this problem, such cause, that was the cause, FA. That was the reason why there is a distortion. That distortion will be reverted back by using a reverse magnetic field generated by interpoles. Okay, let's revert it back. Any magnetic field from here to here is magnetic field, you know from N to S. So inside the magnet, it is from S to N. Assume that here's a permanent magnet. Magnetic fields lines are N to S outside the magnet, but inside the magnet, it is from S to N. So here is S and here is N. Houston, push magnetic field up. Push magnetic field up. So these MMF must be reverted back by NS by excuse me, NS. Here's something wrong. Is it? Excuse me. Just reversed. Okay. Just reversed. New. And S. Here's S pole. Here's N pole. You see N ve S. N and S. Let's take care in the figure. N and S. N, S. Take care. N, S. That is just reverting the reason. That was the reason. So we have cancelled the reason. As a result of this design, sparking will be reduced. Let's take care.
Fields oppose the fields created by armature reaction.
There's a sparking.
The neutral plane is moved back toward the correct position.
Now there is no sparking. But here's something more. Another design is using commutation winding. Commutation winding. Excuse me, compensation winding. Let me write it down here. Here you see some winding. The reason, this guy interpoles corrects magnetic field lines in the mid of armature. The correction is applied to the mid of the armature, Houston. But there is still some realignment here, caused some realignment. those field lines will be up here. Again, that guy will cause some position change, some dense regions here and here. Even if interpose corrects sparking problems in the commutator brush mechanism, the distortion on the pole shoe will maintain. There is no precaution yet. There must be a better design to overcome this problem. Yes, there is another approach using commutator compensation winding. That is the compensation winding. Let's take care. Compensation winding. So let me draw it down here. Here's the pole. Here's the pole face. Pole face. Pole core. Pole core. Pole face. Pole face. Generally, we say totally it is pole, but pole is constructed by two parts. One is pole core, the other is pole face, and over the pole core here's a field coil. Okay, ladies and gentlemen, there's a new design, a better design. Here are tiny slots. There are even number of slots. Let's say 6 here and 6 here. And the reason is here. Magnetic field lines reverted here. So we should overcome this issue. We should push magnetic field downward here. So we insert some conductors here, carrying some winding. Let me say A to A prime, B to B prime, C to C prime, D to D prime. They are the winding looks like this, from here to here, here to here, and here to here, and here to here, here to here, here to here. And the current's direction is important. Ladies and gentlemen, here must be dot, cause some magnetic field lines like this. Here they are cross. Cross means here's such a flux distribution, and such distribution will revert magnetic field back. So magnetic field initially, I will clean after drawing. Initially magnetic field was distorted like this, gentlemen, and then after having those winding, compensation winding, magnetic field lines will revert it to its original shape. Compensation compensation winding. It's called as compensation winding. Will revert magnetic field in whole shoe to its original position. Okay, when you push it to the original position, again, commutation will be easier. You eliminate sparking. You eliminate wear out here occurring on brushes. You eliminate some what was it? Caused some interactions. You have seen a radar screen here. It interfered to some other electronic signals. So you have eliminated sparking, and you have eliminated some other electronic problems in the circumference. You see no reaction right now, no sparking, because right now magnetic axis is in line with geometrical neutral axis, so it is in its original position.
In addition, to further counteract armature reaction, windings called compensating windings are sometimes placed in the main pole faces. The current in these windings is armature current flowing in opposite direction to the current in the armature conductor.
Now, here we have learned two different methods. One is using interpoles. First method was using interpoles. The second method was using compensation winding. Here you see that mechanism must be adaptive. Armature reaction effects must be cleared out adaptively. If there is high armature current, there is high armature MMF and worse armature reaction effects. Houston, we've got a problem. So, the precautions from with interpoles and compensation winding must be adaptive. So there's a smart design. We use armature current in interpoles and compensation winding. Ta-ta! Aha! Yes. Here's armature current. Armature current supply interpole. Armature current supply compensation coils. Those are armature 1 and armature 2. Those are armature terminals. Interpoles, compensation windings, but they are not drawn like this. In fact, they are generally shown like this. Let me show you. Here's dynamo, let's say, DC. That is the armature. That is the main field coil. let's say in old style A and B, those are A and B, and here you see let's say I and K, let's say separate excitation. We will talk later, separate excitation terminals, I and K. In new literature, they are F1 and F2, A1 and A2. For the compensation and interpole windings will be shown here, connected into series. It is G and H, but in new machines, in new designs, we call A1 and A2 here, all including interpoles and compensation winding. Because those windings are designed to eliminate adverse effects of armature reactions, so they must be used. Some laboratory machines, that winding will be separated to distinguish the effects done by this winding. So it is drawn here. But today, if someone say, here is A1, A2, here is F1, F2, those are field windings. Here is dynamo, armature coils. And those precautions are added into the armature. That is the general case. There is armature compensation and interpoles in the under the terminal, inside the system. Okay. You should read the data sheet of the machine if there is compensation winding or interpoles. They are not the general case. The first precaution we made is using interpoles. That is the first one. Second one is using compensation windings. We use compensation winding especially in very large systems, very large motors. And then there's a first or zeroth method is changing brush position. Okay, let's take care here. There was some distortion, there was some sparking, and then we have changed the position of the brushes.
Sparking may cause severe interference in nearby electronic equipment. There are two ways of maintaining the neutral plane in its correct position and thus avoiding sparking. It may be done by the adjustment of the brush position. The brushes are adjusted to lie in the adjusted neutral plane.
As you see, we have adjusted a new neutral plane. We have changed brush position into new neutral plane, and you have eliminated sparking. That is the first thing you can do to eliminate sparking. But here would be some distortion, continuous, And here would be some saturation. Again, there is a distortion, but you only eliminated sparking. But the position will change by the magnitude of current. If there is a severe armature reaction, so you should move brushes much more further. If there is a small amount of armature current, there's a small amount of armature reaction, so the position change will be smaller. The change must be adaptive with respect to armature reaction, and it is difficult to maintain. To overcome this problem, another design is using interpoles. Here you see interpoles.
The neutral plane is moved back toward...
Neutral plane is moved back towards to its original position.
The correct position.
Correct position. The other method is using compensation winding to overcome the rest of the problems. Rest of the problems, saturation problems down here. All those are adverse effects of armature reaction. Okay, you can follow this video. It is 34 minutes. It is very clear to understand. Only take care of the current and electron flow direction. So, gentlemen, remedies or designs, precautions, remedies to decrease armature reaction effects. Armature reaction caused some magnetic field distortion in poles and in neutral planes. Here you see, in the neutral plane and in poles, there were some distortion. Here you see, here's a distortion, here's a distortion. There were two main adverse effects. And then to overcome this problem, what can you do? What are the remedies? Here are the remedies. I have mentioned using interpoles, using compensation windings, and some other passive methods. Also, there are some other passive methods, but not enough. This one, for example, can be used. Slitted pole design. Slitted pole design means here's a pole, pole shoe. You know, here were crosses. That crosses cause such a field distortion, field component causing distortion. That was the field distorted. And then, Houston, take care. By making a proper design on this pole shoe, that is pole shoe, it is slitted. Here are slits. Slits. Slit. Yarık demek slit. Slit. Slot oluk demek, daha büyük. Slit bunun incesi. Genellikle içine bir şey koymak için değil. İçi boş. Here are slits. Slitted pole shoe design will be used. Slitted pole shoe design. Now, such a design makes reluctance of this path larger because you add some air gaps. So air gaps, reluctance is larger. Fa over reluctance of this path, if reluctance increases, flux will be decreased. So distortion will be decreased here in the pole shoe. Yes, it is a better design, but not bring out all the solution. In large machines, they are must. Large machines, those two are must. But in the history, those two are also used. Now, for example, you can also make some other use of special pole tip design. Okay, what does it mean? That is the second solution, slitted core. Let me change color for the first one, orange. Special pole tip design. Here you see magnetic field lines are reverted to the up, here. So we should push such magnetic field to the down. How can you manage this? There is an old method. Let me special pole tip design. Yes, here it is. In the orange one, special pole shoe. Magnetic field lines was reverted to the up. Here you see. You should overcome this. How can you manage it? Okay, let me make a special arrangement. Here's the pole tip. Here's rotor. Houston, what is happening there? For example, large distance, smaller distance, non-uniform air gap will be non-uniform, asymmetrical air gap is designed. Here you see a larger reluctance on the upper corner. Here you observe smaller reluctance. Magnetic field lines prefer to move towards the lower reluctance. So these field lines will be reverted back by using such a design. But Houston, take care. Machine operation must be fixed. For example, it was generator and rotation direction and EMF polarity must be fixed. Houston, for example, if the polarity will change, for example, if you change the rotation direction of the armature, so in such a case, magnetic field lines will be reverted to the counterclockwise direction. Houston, magnetic field lines will be like this. Oh my gosh, yeah. So if you apply the first design rule here, something must be fixed. So it is the usage of this approach, is not common. It can be done, but it is not common. Sometimes we prefer some high reluctance paths. There will be some different designs. For example, the effective air core, area core will be smaller here. There is a different design. You have such a metal sheet, and then you use one this, the second one will be reverted down to here, the third one will be packed like this. So all sheets will be packed like this. Effective core area will be decreased in edges. Effective core area and reluctance. Effective core area will be reduced, and it causes reluctance increase. So magnetic field lines never prefer pole tips. That is pole tip, uç, pole tip. It is not common. Here you see. I haven't seen such a design. It was prior to First World War. In warships there were such designs, but later in professional systems we always use first the third approach and then the fourth approach. Third and fourth are common methods today. For today. Common. Okay. Ladies and gentlemen, here you see slitted design. Slit. Here you see slits and slots. It is a bit slot, but slits are generally more thinner. Those are, but here it is slots. It depends the engineer's choice. In fact, it is difficult to manufacture. For example, the guy make a pole shoe design, and they also use that design. Let me install compensation winding here, for example. Compensation. Let's install compensation winding here. From here to here. And then from here to here. And then from here to here. And then from here to here, and then from here to somewhere here, from here to somewhere here, excuse me, change back to green, from here, and then magenta, purple, purple, and then pink. You see symmetrical construction. Symmetrical. Half of the coils will move to the left, half of the coils will move to the right. So it looks better. Used copper will be less by using such an arrangement. That will be compensation winding. All those, that is auxiliary pole, you see, interpole, that is main pole. All the armature reaction reducing elements, interpoles and compensation windings, will be connected into series and supplied by armature current. Armature current. Supplied by armature current to overcome adaptive armature reaction remedy. To overcome armature reaction problems adaptively. Interpoles, here you see interpoles again. All those coils are connected in series. Sometimes we say interpole, sometimes we say auxiliary. Auxiliary yardımcı demek, interpol ara kutup demek. İngilizce'de daha ziyade auxiliary geçiyor, interpoles geçiyor. Türkçe'de auxiliary diye tercüme etmişler, yani yardımcı diye tercüme etmişler Türkçe'ye. Yani interpol daha yakışıklı oluyor ama yanlış değil. Türkçedeki kitaplarda auxiliary diye de geçiyor. İngilizce'de de az miktarda auxiliary geçiyor. Compensation winding. Az önce ben yapmıştım. İşte here you see main poles. Here's the interpole. Sometimes we say commutation pole or auxiliary pole. Commutation pole, auxiliary pole. And here are compensation windings. Those are compensation winding. The course is about to getting to end. The compensation winding will look like this. That is main, from here to here, main pole. That is interpole. Here you see. Let me change color. Interpole, that guy. And here are compensation windings. From here to here, I said it is symmetrical. 3 to the left, 3 to the right. Here you see 3 to the left, 3 to the right. It is symmetrical. That is compensation winding. Compensation winding. Compensation winding and interpoles are connected series, and the winding is connected to armature in series. Let me show again. Here is the armature. Let's say dynamo or motor, it doesn't matter. Today it is generally motor today. The dynamo usage is very rare today because DC can be easily get by rectifiers. That is the armature. Here's another coil called as GNH. That is interpole plus compensation winding. Here are the two major terminals. Here is the field coil, let's say INK. Today, generally, we use those two, A1 and A2. The compensation and interpole windings are connected in series together with armature, and then finally we got final terminals here. So as you see, armature current adaptively correct armature reaction adverse effects. It moves brushes to the original position. It moves magnetic field lines to the original position. So armature reaction effects will be removed. Here you see much more compensation windings. Main pole, main, interpole, interpole. Here you see interpole. Here's the main pole from here to here, here to here, here to here. It is sometimes difficult. Main. That is auxiliary or interpole. Interpoles. And here you see Houston. Let me show you. Here it is. Some of them to the left. Some of them to the right. They are symmetrical. Those are compensation winding to overcome armature reaction effects. And this topic, I will say a few things later, but not important. I will not enter deeply. That is the problem causing spark. So if you make good remedies, good designs to overcome armature reaction, so major issues will be solved for commutation. Commutation. I will not enter deeply this topic, so you are not responsible commutation problems deeply, but the same remedies will work for commutation. Adjusting brush position, yes, we talk about this. Interpoles, yes, it makes easy to commutate the current in the coil under the neutral axis. Compensation winding, again, that was one of the methods to eliminate armature reaction adverse effects, and now it makes easier to commutate current in the coil under the commutation. Şurayı Türkçe söyleyeyim. Nötr ekseninde fırça tarafından kısa devredilen bobin akım değişimine girmektedir. Bakın, şimdi burada yukarıya doğruyken şurada kısa devrediliyor ve burada da ters yönlü akım geçiyor. Bu dI bölü dt ayrıca bir takım problemlere sebep oluyor. Yani dI bölü dt demek dfi bölü dt ve bu kısa devredilen bobinin etrafında tekrardan ikincil bir gerilimin düğümlenmesi ve o gerilimin fırça tarafından kısa devredilerek burada fırçayı yemesi hadisesi vardır. Bu da yine bir komütasyon problemidir ama siz manyetik nötr eksenini olay yerinde fırçayla aynı eksende tutuyorsanız o zaman bu komütasyon problemlerinin de çoğunu halletmiş oluyorsunuz. Gerisi halledilemeyecek detaylara biniyor. Açıkçası armature reaction efektleri düzeltmek için kullandığınız bütün yöntemler burada ana problemi kaldırınca komütasyon da kolaylaşıyor. Komütasyonun bir zorlaşmasının başka bir sebebi daha var. Bu da bu sargıdaki zaman sabiti. Yani burada bir R var, bir L var. Bu R'ler, L'ler bir zaman sabiti yapıp akımın değişiminin tam kısa devre anında sıfırdan geçmesini bazen bozabiliyor. Ya tam kısa devre olduğunda akım sıfır olsa o zaman hiç ark çıkmayacak. Anlatabildim mi? Şu fırça şimdi mesela buraya basıyor B'de. Burada sorun yok. Ama şu ortaya bir yere geldiğinde mesela bak fırça buraya gelmiş olsun. Şu bobini kısa devre ediyor. Şimdi eğer akım artı yüzden eksi yüze atıyorum. Sıfırdan geçiyor kısa burada kısa devre anında ark oluşmuyor. Tam ideal komütasyon olmuş oluyor. Tam değiştireceğin zamanda akım değişmiş oluyor. Ama sargıların RL dizaynlarından kaynaklanan bir takım zaman sabitlerinden dolayı akım gecikmesi oluyorsa incomplete commutation yani zamanında tamamlanmamış değişme işlemi en sonunda size bir arklan dönüyor. Şurada da orada da bir arklan dönüyor. Bunun dizaynı çok kolay değil. Sargıların RL'sinin dizayn edilmesi gerekiyor. Çok meşakkatli bir iş. Evet, branch position, interpose, compensation windings, all those methods will eliminate armature reaction as well as commutation problems. I hope you got the main ideas.
That's the end of today's course. Thank you for joining the class.